In this video, we now turn our attention to second order differential equations, and we're going to focus on the ones that are linear, right? We saw in the first order case that the linear differential equations, they had a fairly straightforward method of solution, and I think you'll realize that that's also the case for the second order. So what we're going to do in this video is just give some notation, some terminology, and a little bit of theory behind these second order linear differential equations before we actually start looking at methods of solutions, right? So a second order linear differential equation has the following form, right? So what do they look like? Well, I'm going to write down what's sometimes referred to as like a standard form. There are kind of two standard forms that this type of differential equation has. I'm going to start with the first one, and it looks like this. So you have a function of x times the second derivative plus another function of x times the first derivative, and then another function of x times y, and then you could potentially have a function on this side. I'm just going to call it f of x, right? And so much like the linear first order differential equations, as far as the dependent variable and all its derivatives, we can't have terms that involve these functions with non-linear functions. So for instance, they can't be squared, or I can't take the square root of one of these, or I can't have the sine of y, for instance, right? But what I am allowed to do is I'm allowed to multiply by coefficients that involve the independent variable x, right? So there's our independent variable, again independent variable, and then here independent variable, right? So that's the most we can do. So let's write down some specific examples so we can see. We'll start with some that are linear, and then some that aren't linear, right? Say if I have something like x squared times y double prime minus e to the x times y prime plus the cosine of 2x times y, and then this side I have the square root of x plus 1. This is a linear second order differential equation. You know, we look at the coefficients, the x squared, the negative e to the x, the cosine of 2x, and these are all non-linear functions. But that's fine, because these non-linear functions, they only involve the independent variable x. They don't involve y. So something like this is linear, right? Whereas if I have something like this, let's say I have y squared times y double prime minus y prime plus the natural log of x times y is equal to 0, then now this one is nonlinear, because look, right here there are two things that are going wrong. First, I have the dependent variable squared, so that's a big red flag. Second, I have the square of the dependent variable times the second derivative of the dependent variable. So I can't have a function of y multiplying y or y prime or y double prime. So this is like a double whammy right here. So this is nonlinear, right, for this reason, or these reasons, I should say more precisely. All right. And again, so we're going to focus obviously on the linear ones, but even of the linear ones, ones where you have coefficients like x squared and e to the x and so forth, these are very, very difficult to solve analytically. Like if we wanted to come up with either an explicit or implicit equation for our solution, very, very difficult. So these even aren't the ones that we're going to actually solve, but we need to know a little bit about them in terms of when there is a solution and so forth. All right. Okay, so let's So now that we have a way of identifying when the second order differential equations is linear versus nonlinear, there are two standard types. Now, the next method of classification that we're going to do, it involves a familiar word, right? It's a word that we did with linear systems. It's a word that we used with first order differential equations, and we're going to use the same word with now second order linear ones, right? And it's in reference to this function on this side. So if the function on the right hand side, so when it's written in this particular form, right, if that function on the right hand side is identically zero, so in other words, you essentially have the zero function on this side, right? So if the function on the right hand side is identically equal to zero, we say the DE is, and what is this overused word? Homogeneous, right? And yes. So what I would say is this use of the word homogeneous is fairly consistent with the way we used it in linear systems, where if the constants, right, on the right hand side are all zero, remember in our linear system, we classified those as being homogeneous linear systems. Same thing here. If the function now on this right hand side is equal to zero, we're going to classify this type of differential equation as homogeneous, right? So otherwise, right, if your function is not identically equal to zero, so if you have a non-zero function um, over on the right hand side, then we say the DE is non-homogeneous, right? And in fact, these two examples illustrate both of those ideas. So this first equation here is linear and it is non-homogeneous, right? Whereas this one is non-linear, but it is homogeneous, right? So again, because on this side, the function is identically equal to zero. So this one would be homogeneous, right? Okay. So now what we're going to do is state an important theorem regarding the linear differential equations, second order. Whether non-homogeneous or homogeneous, this theorem is actually really useful because it gives us sort of a guarantee as to when these equations will have a solution. And that's what we want, right? We don't want to start developing methods of solution only to find out, oops, there is no solution, right? So in order to state this theorem, the theorem can be stated in if the differential equation is given in this particular form, but it's actually a little bit easier to state if I rewrite it so that the leading coefficient is 1, right? That seems to be kind of an important form of all linear differential equations. We saw it in the first order, and now we're going to see it again in the second order. So this is what we're going to say. If I take this function and I divide all four terms by the leading coefficient here. So let me call this equation 1. So dividing equation 1 by that leading coefficient a2 of x, it gives this equation. So I'll have a leading coefficient of 1 there, but then I'd have to go ahead and divide all these functions by a2 of x. So I'll have a1 of x over a2 of x times y times y prime. So y prime, and then plus a0 divided by a2 times y, and then I have my f function on this side divided by a to x, right? So it looks a little messy when you do that. So what we're going to do now is let's go ahead and relabel these functions, right? Because these are like arbitrary functions as it is, right? So there's no real need to label the top and the bottom differently. So let's just rename them all together. So let's call this one p of x. Let's call this one q of x, and then let's call this one, we could call it like r, or I'm just going to call it like g of x, right? It doesn't really matter, but it's simpler. Instead of keeping these, kind of cumbersome looking expressions, let's just relabel it and say after we divide through by the leading coefficient, whatever function is multiplying y prime, we're going to call it p. Whatever function is multiplying y, we're going to call it q, and whatever function that happens to be on the right hand side, we're just going to call it g. So that gives us this differential equation, right? So y double prime plus p of x times y prime plus q of x times y, and then now I have it equal to g of x, right? So this is another standard form of a second order linear differential equation. So the theorem that I'm going to state will make reference to these three functions, right? Now, before I state the theorem, now when you're dealing, and we saw this previously, that when you're dealing with second order differential equations, if you want to find a particular solution, then you need two conditions, right? So this differential equation, right? Right, so this is our differential equation. To determine a particular solution, right, two conditions are needed. Right? And if we require that they're initial conditions, then what it means is we would have to know the original function value and the first derivative value at the same value of, in this case, x, right? So two conditions are needed, and I'll say usually, and these are defined at the same value of the independent variable, right? And we still refer to these as initial conditions, right? So, and these are referred to as initial conditions. So what do they look like, right? Well, in fact, let me write the DE yet again. I could do this with my eyes closed, right? And then we might have something like y of x0 is equal to, and then I'm just going to call it like a, and then y prime of x0 is equal to b, right? So now this would be our initial value problem. And again, we've seen initial value problems like this that involved the second derivative, but they weren't of this particular form, right? But we've seen conditions that looked like this that allowed us to find a particular solution when we have a higher order differential equations, right? So what we would like, so the theorem we're going to state now is going to give us a guarantee as to when this initial value problem has one and only one solution, right? So here is our theorem, and it is existence and uniqueness theorem. And we saw one for the first order. Here's another one for the second order, right? So it says, so I'm going to refer to this now as 2, right? The initial value problem, so the initial value problem defined in 2 or given in 2 is guaranteed to have a unique solution whenever P, Q, and G, so whenever P of X, Q of X, and G of X are all continuous on some interval that contains x0, right? So whenever P, Q, and G are continuous on some interval containing that initial value of x, so in this case containing x0, right? So what it comes down to is, again, it's a property that we have quite, the experience with. We have a lot of experience with identifying where functions are continuous. And now for this type of initial value problem, to have a unique solution, then we want to make sure that this coefficient is continuous, this coefficient is continuous, and then this, I guess you could call this a coefficient too. It's just a coefficient of 1 essentially, but this coefficient also continuous, but just not just on any interval. They all have to be continuous on some interval that contains x sub 0. Once you do that, then we're guaranteed that we will always have exactly one solution to this type of problem, right? And then it makes the task of finding a solution not a futile one, right? So we're finding something that actually does exist. Okay, so let's take a look at an example of how this theorem might be used, right? So let's, in fact, we'll look at an example here. So let's say we have this. Hold on. So let's say we have our y double prime plus e to the x times y prime minus, and let's say we have arcsine of x times y, and then on this side we have x plus 2, right? So here is our differential equation, right? And it is written in this particular form that's required by this theorem, this existence and uniqueness theorem. We can identify the three important functions now. So our P is the e to the x. The Q is negative arcsine. And then my G is the square root of x plus 2. Right? Now, since I didn't give any conditions, let's just figure out what would be the largest interval over which this differential equation would be guaranteed to have a unique solution. So let's figure out the intervals over which all three functions are continuous, right? And in that case, then we know our x0 would have to be in that interval, right? Okay, so let's start with the e to the x. Well, this function is always continuous, right? So e to the x is continuous for all x in the set of real numbers. So there's no limitation on this as far as, well, that would be imposed by having this as a coefficient, right? The arcsine function, however, is different, right? Negative arcsine, that function is continuous You might remember its domain. It's continuous when x is between plus or minus 1. So now that really limits what's going on, right? And then let's see about the g of x, or our square root function. So the square root of x plus 2, that function is continuous when what's under the radical is greater than or equal to 0. So whenever x plus 2 is greater than or equal to 0, if I solve this inequality, it's a nice simple inequality, so this tells me that x has to be greater than or equal to negative 2, right? So by the existence and uniqueness theorem, we have to find the interval that's common to all of them, right? So what is the common interval of continuity? Well, this one is the most restrictive, right? Because so for instance, if we sketch our, let's say we sketch all of these. If I start with the interval of continuity for e to the x, well, it's all real numbers, right? Then if let's say I look at this one, well, this one then removes all numbers less than negative 2. So like that. So yeah, let me take that off. Right, so that's where if I look at this one and then I look at this one, and now if I apply this one, I have to take off even more, because now it's saying that I have to be greater than or equal to negative 1, but then less than or equal to positive 1. So suddenly my interval shrinks down to this, right? So if I were to, first of all, even figure out a way how to solve something like this, and if I wanted to apply conditions to guarantee a unique solution, one and only one solution, I would have to pick an x value in this interval to write down my condition. So for instance, I could pick x equals 0, which is a typical value for initial conditions, right? So let's write this down. So to guarantee a unique particular solution, right? The conditions, or let's say the initial conditions, where I have y of x0 is equal to some number, and then y prime of x0 is equal to some other number. So these conditions, so let's say the initial conditions must involve x0 in the interval negative 1 to 1, right? If I pick something outside of that interval, who knows what will happen? Chances are I won't have a solution, or I might have some weird thing where I have multiple solutions. If I want to guarantee just one, my x0 has to come from this particular interval. All right? So that's just a little bit of theory behind these linear second order differential equations. We don't have such a theory for the non-linear ones. The non-linear ones are just, because they're so, they're not so restrictive in what form they take, it's hard to develop a single theory that refers to all of them, right? Similarly, in terms of solutions, which we're going to get into our next video, again, once you restrict it to a particular type, the method of solution is very, very straightforward. If you don't have it restricted like that, then it becomes a lot more difficult, right? So to see what we're referring to and to see how we solve and what type of these equations we're going to solve, why don't you tune into the next video? I'll see you then.